Okay, so let's talk about updating the ICP function for absolute orientation. So we had our ICP function overall, and what I realized is that, and what we talked about is that we weren't really using the rotation and translation there overall for what would happen. We basically did it on a local basis. So I wanted to show you how we can actually change that. There are multiple strategies that we can do that to perform the absolute orientation, meaning that if we give it a particular point or a particular point cloud and your STL model, what would be the final rotation that and translation that takes that original point to your STL model? And we basically tweak the original algorithm just a bit so that instead of the relative orientation, we can get the absolute orientation from the point cloud to the model. So let's go through it. So basically, this is our ICP point STL. So instead of that, there are really two ways that we can perform that. Either we can do the rotation and translation every iteration, meaning that we can have some intermediary variable and then say, okay, we can get the rotation and translation that we have, that we're updated the scan x_scan r. And if we have our rotation and translation at every time, we can just basically create a particular intermediary variable and update our rotation and translation at every iteration. There's no real problem with that. There's an opportunity, but what I would like to do is I would like to basically, because our x_scan gets updated, I want to basically introduce an x_scan there so that we can afterwards just call it back and then get the absolute rotational orientation at the end. So here I'm just saying every time x_scan r gets updated, and hence the rotation and translation calculated below, basically here, is the rotation and translation of the final relative rigid body transformation, basically by means of the updated x_scan and what we have here as our x_BIM. That means that we don't completely get rid of the x_scan r that we had, or our original one that we had, that we put there. This way we initialize x_scan r exactly the same way that we did. So the algorithm can go exactly there, but we still have the x_scan here. And what is beneficial here, that once we have our x_BIM, then we can reintroduce this on the bottom, just this same formula, but instead of x_scan r, we just do x_scan. And then we find the basic solution. So this helps with that introduction of that and finding the absolute orientation between before the ICP and after the ICP. And this would be beneficial not for this session, but for the next session when we're going to talk about the tolerance checks. We just copy basically line 25 here, go down. Really, the RMSE is not important for us because the RMSE is what we have for the last iteration when we're actually comparing the last final one. But the rotation translation is important because we want to see how much rotation translation was there between them. And really, the RMSE shouldn't even matter because that would basically provide the same results overall as well. The original algorithm, if you had observed the original scan versus BIM, was that in every iteration, our registration, our distance threshold is actually updated by means of the RMSE of the registration from the previous state. And not by means of itself, but by means of the maximum of twice of the RMSE and our original distance threshold. And the reason why it's twice is because they wanted to introduce a 95% confidence. Basically, it's 2 sigma for our normal distribution. So that's what they try to do. And RMSE is a measure of your standard deviation. So they try to justify it that way. And I'm basically I'll give you a spoiler. I'm going to show how that has no bearing, and that's one of the reasons why I actually didn't even consider teaching it to you. But I thought it's important for you to know. And basically, I want to show you also another thing here, that if you're kind of saying, what is this threshold, what is this let's say factor, these formulas, what would they do? This is how you check for it. You basically do it very simply, and then afterwards, when you want to recheck and see the impact of one particular thing, you just change that one particular thing in your experiments. And once you change that, then you see the impact. Is it impacting? Is it having any problems or not? Okay. So how they said that every iteration that this underlying threshold changes. So what we do is, again, similar to what we had there, especially when things are changing, we just introduce an intermediary variable there. So we introduce something called basically an intermediary variable, so that we can put that particular distance threshold in an adaptive stage, that every time it improves, rather than just that original one that we had. And I've put here, it may be beneficial to update the distance threshold. So what you do is basically you use it as basically the RMSE. Essentially what the justification, the logical justification that they brought is that now we're going to use, what if the RMSE is very, very large? And the beauty of it is that for the most part, the RMSE would not get too large, because the RMSE is actually the function of distance threshold. You're going to have exactly this much distance. So it just would not impact it at all. But, you know, they have to make it fancy. So what we do is we just add an intermediary variable there at each iteration to update the distance threshold. So let's call that variable D, let's say underline adaptive, you know, or adapts underline fresh, you know. And this is going to be basically a row vector that we get at the very end. And we initialize our basically the adaptive with our distance threshold, meaning that that would be the first one that we have. And in every iteration, this gets updated. So now what has changed? This D underline adaptive is what we're going to change, right? So this goes directly to the place where we used to use our distance threshold. So the first iteration is exactly the same. It's as if we're using the distance threshold, but we're not losing the distance threshold, because we're using it to introduce that adaptive strategy, which is here. And the adaptive threshold for the distance is basically the way that they defined it. It's maximum of the initial one. So let's just copy this down. It's maximum of this initial one, which is the distance underline fresh, and our twice the RMSE here that we get. So we go and copy this underline fresh, maximum of that, and twice the RMSE. And do that. And basically every time now, see if what this shows is that, okay, we are now initializing the D underline adapt threshold here, okay, as this underline threshold. Every iteration that goes down, the first iteration is going to be the first one, right, which is this underline fresh. When it goes here and we increase the I here, the second iteration, the underline adapted underline fresh would be with respect to our maximum of the distance threshold, which is what we had originally, and 2 times our RMSE. Let's quantify this impact. So let's see how this is actually impacting it or not. So what I'm going to do is, this time, instead of basically, so what I've done in addition, maybe you guys don't have this, that I've added some outputs. This is really for you to see how you want to play around with it. So a function like this, whatever you have as an output here in your calculation, you can put it as an output and see how it is. So you just put comma and the name of that variable that is changing, that is as an output. So for instance, here I added error as well because I wanted to see how the error changes. So you might not have it, you might have it already in your program, but don't get worried. It's nothing special. It's just for me to teach you and to show you how it changes or not. And you can basically decide whether you want to keep it or whether you don't want to keep it. That's the option that you have. So this time I wanted to see really how this adaptive threshold is changing as we changed our distance threshold for our example that we had. And I wanted to kind of do that to see, okay, if we do it basically like this, and we find the maximum of our D underline adapt underline fresh for different variations of this underline fresh, are we going to get significantly different results than our original this underline fresh that we put there? So that's what I'm doing. So here, what I've done instead of that is that I'm going to put this as an output. So what I do is, instead of having it just as a singular, because now that you're every time adapting it, the previous iteration is going to change. So you're going to have one singular value for your D underline adapt underline fresh. This time I want to make it into basically an array. So every iteration with respect to the I, which is the iteration number, it changes. So basically this is how it is. So you have, instead of having it as this underline, D underline adapt underline fresh, we have D underline adapt underline fresh of I, which is the ith iteration that it goes. So this is the ith iteration. This is here the ith iteration. We just added there. Here I just added I. It doesn't really matter. You could just add one, or you can change it, leave it exactly as is. Because when you assign something the first time, it basically goes to the first array as well. It doesn't matter. But here, the good thing is that we've already introduced I as equal to 1. So if we go D underline adapt underline fresh I, that means D underline adapt underline fresh of 1. That means the first element. So here, I want to show that. So I want to see how that changes. And I want to play around with the this underline fresh as well. Here you just have to, the I you have to remove here. And you know, sometimes it kind of shows whenever you see this red thing here or on somewhere, you kind of have to take a look at that line and make sure how it is. So if I were to have done it with I, there's no definition of I really. So if I say D underline fresh underline adapt underline fresh I as an output, there's no definition for that. There's no meaning behind it. So it gave this nice thing here. So when you just remove that I and put it as D underline adapt underline fresh, you're now good to go. And here, what I wanted to do is I just wanted to, from now on, utilize, instead of the rigid body transformation that we had initially, let's just transfer to our horns method. And what we want to do is we want to just change this for the horn points. The difference is that the destination and the source has been changed in the horns, basically the one that I have provided to you. You can, the good thing about these being as a function, you could yourself change the output, the input. So you can say, instead of the destination, you can put the source and so on and so forth, so you can have that consistency. But as it stands with the one that I have provided to you, this is how you go about it. And then there's a W function there as well, a variable. That's the weight function for every point. So imagine if you had the error associated with every point. You knew that this measurement error for a particular point is more or less. If it's very, very high, then you can actually utilize that to kind of make the weight of that point so low that it doesn't bear any impact on your final results. That's the whole point of that weight function. For us, we don't use that really. So what I did is I've put ones of the length of ID BIM and 1, basically a row of 1 as our W. I wanted to just showcase it with you so that you can see what I mean. This is basically for the assignments, how it is. So, and the STL file format is basically that assignment mesh, right? .stl. and distance threshold and RMSE threshold. So here I want to kind of this, if we put it as 0.05, and let's do this like this. Let's like enter. You're going to observe that the D underline adapt fresh, if you go there, is almost always going to be 0.05. Only in the second, it kind of increased slightly. But the rest is really, really the same. That means that because the last iteration was also 0.005, it would have almost no bearing on the final results at all. So making it adaptive or not, it didn't really change anything. So what I was curious after this that I want to go through it with you is that let's see how if we put the maximum of all of this adaptive threshold for every iteration with different levels of D underlined fresh or distance underlined fresh from 0.05 to let's say 0.3, I think I've changed it there. And for this part, I don't want you to actually do it here. I want you to check it later on at home because it's going to take a while. And this underlined fresh, which is this value here from 0.025 to 0.35, how the maximum of the underlined fresh changes. So if I want to do it in, let's say, increments of 0.025, how I write this is that I start from the first one, 0.025, in increments of 0.025. That's just my assumption there. So I'm just changing that there. So I put 0.025, which is the first. The second is the delta, which is 0.025. And then the third part is the 0.35 that I have there, which is the final. So that means that I now have an array of this underlying freshes that start from 0.025 in 0.25 increments to 0.35. So if you go ahead and let's say enter that in increments of 0.025, it gives you a row vector. So it starts 0.025, which is our starts that we wanted to see, 0.05, 0.075, 0.1, and so on in 0.25 increments. So what I want to do after this is that I want to basically perform this task every time with each and every one of these. Okay, so I'm going to do a for loop. So I'm going to do for 1 to 14, which is the length of this underline fresh. I'm going to say in this, I'm going to basically run this. And instead of the 0.05, I'm going to do this underline fresh of I for that particular iteration. And then I'm going to measure what this the underline adapt underline fresh is. And I actually, because that is also an array, I'm going to get the maximum of that. Just so that you can see the maximum that you can get of this underline fresh is actually going to be your the adaptive is actually going to be your this underline fresh. So there's no reason for you to actually change that or perform an extra step that every iteration is going to add to your calculation. Now, if you maybe change the factor of 2 to factor of 3 and 4, maybe that changes, but that really requires some justification. Anyways. So we basically perform a for loop there. So for I equal 1 to length of this underline fresh. So this length is 14 because it's 14 values. So at every time I want to basically do this, but with this, I want to basically change this to our this underline fresh of I, because that means that it's the distance threshold for the ith element. Right? Because I've changed that, so I want to see how that change is impacted. And I just changed that so that, you know, it has some differences in case we want to actually check it, but it doesn't matter because we're not really using it. But for good part is a good thing. So now, after I enter that, I actually want to introduce a max underline this underline fresh. And that is basically what we're going to get, which is the maximum of the D underline adapt underline fresh at every iteration. So that D underline adapt underline fresh is going to be multiplied by means of every iteration of your ICP. You remember that bottomneath there. So this is now the maximum of the underline adapt to underline fresh. That means I want to see in all of the iterations for every part where we add a particular distance threshold, for all iteration to convergence for the ICP, how would that the maximum of all of these adaptive thresholds that we're adaptively changing every time, how would the maximum of that change? And basically by the power of TV baking, I basically pause this, and I like these cooking shows, I now bring it out of the oven so that you can see how it looks. And how it looks is interesting because when it's very, very small, it has some bearing, but really when it goes larger, and it's funny because when it's small, it actually isn't the right threshold anyways, because for this, we established that somewhere between 0.15 and 0.3 is really where you're going to see the significance if you use the original, not if you've translated or rotated it. So even these thresholds are already incorrect as well. However, it's still the bearing is not as much. But really, when it matters, this underline fresh and the maximum of all of the adaptive one at every iteration is almost the same. So really adaptively changing it, at least for this example and for many other examples that I've actually worked with, it really doesn't significantly impact the results. It doesn't impact the results enough to even want to consider it. What it would be important, if it's possible, if we actually know the proper distance threshold. If we do know the proper distance threshold, then that has some bearing to it.